Here's my solution. I ended up running this code for quite some time, and I don't expect you to do that. But even if you ran it for a little bit, you should start to see some of the same patterns in our generated samples. Okay, so first I'll quickly go over what's happening in the training loop. First, I'm loading in all my images. The test images will strictly be used for generating samples, so those are fixed here. I'm also scaling my fixed x and y to pixel values between -1 and 1. And you can actually call next again to get a different set of test data if you want. You'll notice that I'm also grabbing an iterator for our training data, and that's because I'm going to set up our batch loop a little differently than before. I'll have to iterate over batches of x and y image data in the same batch loop. So first, I'm calculating how many batches we'll go through per epoch, and that's just the length of a data iterator. Here I'm taking the smaller number because the number of x and y images we have is slightly different. Then we have our usual epoch training loop, and inside, instead of our typical batch loop, I have code that will reset or recreate our x and y iterators at the start of each epoch. So this is going to be when the epoch has reached the last batch in our iterator. So I'm not creating another loop, I'm just making sure that I can call these iterators an appropriate number of times to iterate over all the training data. Or perhaps not exactly all, but an equal amount of x and y training data. Okay, great. So this all was given to you in the exercise code. Okay, then I can use my iterators to get my real x images and real y images. And I'm scaling those as well to make sure they're in the pixel range -1 to 1. Okay, great. So all of this was given to you in the exercise code. Then I'm starting training with my discriminators. I'll go over one example in detail here, dx, and this code should look familiar. First, I'm passing in scaled real image x data and storing the discriminator logits. Then I'm using my real MSE loss that I defined above to get the real loss for the discriminator dx. Then as a next step, I'm doing something similar, only generating fake images to pass to the discriminator. So I'm getting fake x images by passing real y images to my g y to x generator. Then I'm passing those into my dx discriminator and calculating the fake MSE loss. Finally, I add the real and fake terms up and perform backpropagation and optimization using my dx optimizer. The next few steps are doing the exact same thing, only for dy and the dy optimizer. First, I'm training it on real images and then on fake images, adding those up and performing backpropagation. Alright, then to training the generators. I'll go through one example in detail again, gy to x first. The first couple steps here are going to be our typical adversarial loss. So first, I'm using the generator to make fake x images by passing in real y images. So these fake images should look like they've come from domain x. Then I'm looking at how our x discriminator responds, only this time I'm using the real MSE loss function, because this generator wants to fool the discriminator into thinking its fake x are actually real training data. And I'm saving this as gy to x loss. Then comes the new part, calculating the cycle consistency loss. Here my first step is to actually take the generated fake x from above and pass it to my other generator, gx to y. This should return a reconstructed y. And remember that the goal is to get the original and reconstructed images as close as possible. So then I calculate my reconstructed y loss using my cycle consistency loss function. Here I'm passing in my original images y, the reconstructed y, and a lambda weight equal to 10. And I got this value by looking at the training details in the CycleGAN paper. Then I'm doing the same steps only with gx to y's adversarial loss and reconstructed x images. At the end of all this work, I'm adding up the adversarial and reconstructed losses that I calculated to get my g total loss. Then I'm performing backpropagation and optimization using my g optimizer. And then I just have the provided print statements and sample generation code here. Now again, I trained for a really long time, for 4,000 epochs, and I don't expect you to do the same thing, but I do want you to check out the loss patterns I saw. I find it easiest just to look at this graph. So my total generator loss is here in green, and then my discriminator x and y are here in blue and orange respectively. I can see that generally my generator loss is much larger than my discriminator loss, which I expect since it's a big summation of terms. I also see that the generator loss decreases a lot at the start of training. This is likely because it starts off producing really bad fakes, then it makes some big improvements, and then has to sort of refine over time. I also see this kind of squiggly up and down behavior that's typical of adversarial networks. I should also see that at most points my discriminators have similar loss values, that look to be slowly but surely decreasing. At one point, quite late in training, it looks like the generator learned an important trait, and so the discriminator losses shot up here for a moment. And just looking at this, I know I could have trained for a longer time because there's no clear plateau yet. Alright, then let's look at some sample generated images. Here I have a function, viewSamples, that displays samples given an epoch. And the samples are going to be side-by-side real x and their transformations to the y domain, or vice versa, and you'll see what I mean. So here I'm viewing the samples after only 100 iterations. So this is really early on in training. And I'm first showing x to y or summer to winter transformations. I can see my real summer images in the left column, and then right next to them their transformations. So these transformations result from applying gx to y to the original image. And for the most part, they look just blurry and a bit simpler. So a bit of a white color palette, but really just noisy. And here I have my y to x samples, so from winter to summer transformations. These samples look equally noisy, but much more yellow. Next, I'll show you the result at the end of training. So for me, this was after 4,000 iterations, but you should still see improvements after 500 or 1,000 iterations. And here you can already see a great improvement. So these are from summer to winter images. And I can actually see that my gx to y generator has learned a few key things. For example, it seems to have learned to turn green foliage into sort of dead brown foliage. It also seems to turn some surfaces a bit more cool white or gray, so sometimes it looks like snow or just a cloudy sky. I should note also that some images do not undergo much change, and that's because some things will look pretty similar in the winter or summer. So leaving some traits alone and transforming others like the sky and green leaves is kind of a complex idea that this model has learned to distill. I think this kind of model is really exciting, and I think unsupervised deep learning is going to be more important in future research because gathering labeled data is often the most time-intensive part of machine learning. Now, I also want to address some shortcomings of this model, including that these generators can only produce pretty low-resolution images. This can maybe be improved a bit if I just make my images larger in the first place, say 256 by 256 instead of 128 by 128. I think larger images would make these results a bit better, but there would be a trade-off, which is a longer training time. There have been other proposed architectures that improve upon these weaknesses and solve this low-resolution problem, and I encourage you to read about high-resolution GANs. Additionally, these models are best at learning stylistic and texture differences rather than complete shape transformations, which is something to keep in mind if you want to apply this kind of model to a different task. Speaking of which, my favorite resource is the GitHub repository for Pix2Pix and CycleGAN formulations. These models were implemented in PyTorch, and this repository belongs to Junyan Zhu. This is a great resource to use because it uses other datasets and shows you results. You can also look directly at the model code and read it and try to replicate it. I was perusing some of this code as part of my research for creating this lesson, and there are some additional training strategies, like a changing learning rate and other normalization approaches that may make this model even better. So if you like this CycleGAN formulation, try to approach another task like transforming horses to zebras, or doing collection style transfer, or even trying your hand at the Pix2Pix formulation. Have fun learning even more.